Hello everybody, welcome to section 9.5, and we're going to be talking about properties of quadratic functions. And specifically, we're looking at the graphs and some of the properties of those graphs. And so we should be able to sketch the graph of a quadratic equation in standard form. And we want to be able to identify the vertex and axis of symmetry of a quadratic equation, of a quadratic function, finding its domain and range of the function, and determine the coordinates of the x and y intercepts. Additionally, we're going to be looking at the function of the parabola in standard form, which is typically given this way: f of x equals a times x minus h squared plus k, and we'll explain what each of these pieces mean, and use completing the square as a method for rewriting these functions in order to find all of the features of the graph that we talked about. And it will be instructive for us to start by talking about the basic graph of y equals x squared and what that means for us. In this case, I'm showing the graph y equals x squared. We know that what happens on this graph is that, for example, right here at the point where x is equal to 1, y is equal to 1. And when x is equal to negative 1, y is equal to 1 as well. We can also show when x is equal to 2, y is equal to 4. Or when x is equal to negative 2, y is equal to 4. When x is equal to 3, y would be equal to 9. And when x is equal to negative 3, y is equal to 9. And so on and so forth. For each of these points that we identify on our graph, it's very easy with y equals x squared to see what's happening. We say that the point 0, 0, which is the point lowest on the graph, is the vertex of this function. And the axis of symmetry is the vertical line running up and down that passes through the axis of symmetry. So with the most basic kind of quadratic function, f of x equals x squared, we already know some of these behaviors right off the bat, right? Our vertex is given at the point 0, 0. And we would say that the axis of symmetry, which is the line on which, if you were to hold a mirror, would make a reflection that looks like the other half of the graph right there, is along the line x equals 0, right, which is the form of the equation of a vertical line. The domain of this function, as with all polynomials, is going to be all real numbers, whereas the range will be limited by the location of the vertex. In this case, the range can be thought of as the set of all values along the y-axis, where if we were to shine a light against the graph, and here let me just draw like a little flashlight here. Here's my little flashlight. It's supposed to be a little flashlight here. And we shine a light against the graph as though it makes a shadow against the y-axis. We would think of the set of all the y values covered by that shadow as being our range. And in this case, the range is very simply from 0 to positive infinity. Okay, so let's talk about some of these properties that we'll need to know as we're going through and graph some of these equations. So first of all, let's compare a couple of graphs. We have a graph of y equals x squared illustrated here. What happens if we put a negative in front of that graph? Well, as you can well guess, let me go ahead and get my arrow right here. As you can well guess, what's going to happen is that we will get a reflection of the curve as we look up and down. And so it looks as though in this second graph right here, all we're really doing is just showing that for every y value that we got previous to this, our x values are actually going to be shown here as the negatives. For example, 2, we're going to get negative 4. Right? Whereas on our other graph, y equals x squared, hello, mouse. Whereas on our other x squared graph, we're going to get 2, 4. Or if we had negative 2, we'd get negative 4. We get not want that. Uh, I don't want a line. We're going to get negative 2, 4 versus positive 2, 4, and so on. Right? So in these particular graphs, it's easy to see what's going to happen with that. Okay, how about these ones? This, if we have a number in front of x squared, that's going to cause for us a vertical stretch or shrink. And so we can compare, for example, these graphs at x equals 2. The graph of y equals x squared would have gone through the point 2, 4. What would the graph of y equals 2x squared do? Well, the graph of 2x squared would pass through the point here at 2, 8. Whereas if we took the graph of y equals 0.5 times x squared at x equals 2, y would equal 2. So you see that what's happening right here is that that number that we're multiplying in front of x squared is multiplied by the y value we get from x squared directly. So that makes a big difference for us in how we view these graphs. And I'll go ahead and label these graphs here so we can see which one is which. Y equals 2x squared is shown here in orange, and y equals 0.5x squared is shown here in violet down below. We'll note, by the way, that each of these graphs also passes through the point 0, 0. And so in all of these cases, when we're multiplying some constant times x squared, we do not change the location of the vertex. How could we change the location of the vertex? Well, for us to change the location of the vertex, we can either use what's called a vertical shift or a horizontal shift of the graph. So let's talk about each one right here. In our graph with the vertical shift means that we add or subtract some number to x squared. So for example, if I took x squared plus 3, we would be taking the value of x, squaring it, then adding 3 to that number to get the point. So for example, and this graph is shown in purple, at x equals 2, y would equal 7 because 2 squared, 4 plus 3 would be 7. The graph of y equals x squared minus 1, shown here in orange, is a shift downward of the vertex. So instead of passing through the point 2, 4, it would pass through the point 2, 3. Notice what has happened to the vertex, however. Whereas in the graph of y equals x squared, the vertex was at 0, 0. In the graph of y equals x squared plus 3, the vertex is at 0, 3. And in the graph of y equals x squared minus 1, the vertex is at 0, negative 1. Finally, let's look at these two graphs. What about this? This is a horizontal shift. If we add or subtract while we are in the parenthesis right here, I'm going to move these things around because we actually shifted these two things in different places. Adding or subtracting a number inside of the parentheses before we square is going to have the effect of moving the vertex left or right. So let's talk about the graph here in orange, which is y equals x plus 3 quantity squared. Yeah, that didn't work. If we're, nope, doesn't like me here. Yep. Our graph will have its vertex here at, I'm going to zoom in on this so maybe I can get a better fix on the location of that vertex. Well, very close right here. In this graph here in orange, y equals x plus 3 quantity squared, the vertex will be at the point negative 3, 0. And the way you think about that is what value could you put in for x to get 0 out? And the answer is negative 3. Right? So our graph right here should be passing to the point negative 3, 0. I don't know why this one is showing that it is not. Our other graph, y equals x minus 2 squared, would be shifted with our vertex at the point 2, 0, because at 2, 0, what's going to happen is that this graph would be if x equals 2, y equals 0 squared. So we can see that the difference between these two particular functions is that our graphs will shift left or right. So we can use these facts to help us graph functions, which we'll do here in a moment in our next video.